If you want to write that down, I think it's called photons. Yes, photons. Whew. Okay. Good bit to do, and this one's a big one. Yes, 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 a good bit to do. Okay, so I don't know if you've heard this word before, quantum. Is this a word you've heard before? Would you know what it is?
It's like amount, kind of.
It is very good, it is an amount. A quantum, or quanta, is the minimum amount of any physical entity involved. So in other words, it's an amount, but more precisely, it's the minimum possible amount. Example would be, when we're talking about money, the quantum would be 1 cent. This is the smallest amount. What else do we have that's easy? You see, you can't... Shoe size. The smallest amount of a shoe size is a half, because you can go over halves. So it's the minimum amount. So far we had no need for quanta. For example, we don't have a quanta of distance, that is some minimum distance, because distance can be any number. It could be 10 to the minus 10, 10 to the minus 11, 10 to the minus 12, etc. Got that?
Self-control course?
Yes, this would be the context for it, yes. Okay, you have the definition. So a photon is a single quantum of light, and is referred to as a light quantum. In other words, a photon is the smallest amount of light that you could have. So there is light, it turns out, comes in certain amounts, a bit like money. There's the smallest amount you can have, and you can't have any smaller. So photons are what we call like the smallest amount. Okay. You're writing that faster than Musharif. He's going to miss a lot now. We should think of light and other electromagnetic waves as a group of photons. So, I suppose the way we should think about this is instead of thinking, you're back. You missed a bit.
Why?
Why what? Adnan was here ready to go. And I said, maybe we should wait for him. He said, no, go, don't wait for him. You got your mocha and your muffin. Right. If you write really, really quickly, I'll go back one slide.
How many slides did you do?
Two definitions. Faster. Yellow.
Quantum?
Yes. New word?
No.
You know it?
Yeah.
Are you sure? Okay. As I said to Adnan, a quantum is the smallest amount of something that you can have. What other examples do we have?
I think. What is the name of it?
Photons. Photon's.
Then you should make me write that. definition of photon?
That's the next definition.
Okay.
So the next definition is a photon is a single quantum of light. That is, it's the smallest amount of light you can have, and it's referred to as a light quantum. So as I was saying to Adnan, we kind of picture it like this. I know we have our light, but it's kind of better to picture the light as lots of small, many small light photons, light quantums moving through space. So it's almost like, if I put in quotations, photons are a bit like the atoms of light, if that makes sense. It's like the smallest amount of light that you can have. You can't have half a photon, just like you can't have half a proton or a neutron. Okay, so you need this definition too.
So this is bigger. The photon of that, or is it kind of
The atom would be bigger, but photons, I don't think really actually have a size, like a radius. So I know I said they're like atoms, but don't picture them too much as like atoms. Where are you going? What's wrong with your mocha?
I want to share.
Yeah, you don't usually eat anything in the morning.
Me.
Yeah.
But these days, I am hungry in the morning.
Why? Some reason. Okay. Right. So distance. You just to clarify here, you can have some distance, you can have a smaller distance, an even smaller distance, an even smaller distance, an even smaller distance, and so on. But there's no smallest distance. You can keep making it smaller. Yeah.
Point.
But that's no distance.
point? What's up?
No. You can keep making it smaller, 10 to the minus 10, 10 to the minus 11. It can keep getting smaller. But with light, you can have some light smaller, and the smallest then is a photon. But you can't have any smaller than that. So then the next one is no light. So a photon is like an atom of light, which we were just talking about. And there's nothing smaller. So what is a photon exactly? So a photon is a particle of light, that is a single quanta of light. So I know previously I gave the definition, but the definition didn't really say what it is. It only said it's the smallest. It didn't exactly say what it is. So it is what we call a light particle. It's a particle of light. It's, like I said, something that fills the light, that makes it up.
So what is it made of?
Oh, these are all great questions. The material, what's it made of? You'll find out more in the next lesson.
In the exam, if they say try the definition of photon, which one they?
Oh, because the question would be the definition, so it'd be like, what is? So it'd be this one, I'd say. Yeah. Okay. You have this?
Quanta. Quanta is a singular of quantum.
Yeah, I got them mixed up, I think. I can't remember. One is singular and one is plural. Quanta or quantum is plural. It doesn't matter. I'll check the dictionary later.
I'm not sure at all, but yes.
We'll check the dictionary there. Okay. I think I might have had it back. I don't know. Right. So Einstein discovered that the energy of a light photon or other radiation, electromagnetic waves, depends only on the frequency of the light. That is, the higher the frequency, the higher the energy. So it's pretty significant discovery, because if you think about it, if you have a wave, this wave has energy in it. So think about an ocean wave. What would make the ocean wave have more energy?
More force.
Well, yeah, but what does that mean on the picture? So this is A amplitude, and then it's moving with a B, and it has a wavelength. More amplitude, yeah. Right? You'd think that the energy should be a function of the amplitude. Bigger amplitude, more energy. Makes sense. But what is very surprising, extremely surprising about this result, is that for light and other radiation, electromagnetic waves like X-ray, gamma, radio, Wi-Fi, it's not the amplitude, it's the frequency that controls the energy of the wave. And simply, the higher the frequency, the higher the energy. And the formula is something that used to be in chemistry, but I don't think it's in your course anymore. The energy of the light or wave, electromagnetic wave, is equal to this constant called Planck's constant times f, the frequency. And you notice that Planck's constant is extremely small. Extremely small. So even if the frequency is quite high, there's not a lot of energy in a photon. Not a lot. But if you increase the frequency, so you have like X-ray and gamma ray, then you get more energy, and then it starts becoming harmful. So this is the formula for energy of a photon, and this is Planck's constant. This is in the formula book and on your calculator. If you can get this formula, please.
In chemistry, we have formula for energy using H.
Do you? I thought they removed that.
Hc over the wavelength. Gives you the energy.
Hc. Yes, of course, because energy equals Hf. But F, remember, C equals F lambda.
Yeah.
So F is C over lambda.
Okay.
Same formula.
Same formula.
Yeah. The same. Yeah, very good. So you have done it in chemistry. What was the context? Where did you do it in chemistry?
There's no lesson for this. We only explain this formula.
Yeah, but in what lesson, what context?
There is no lesson for it.
She just came in one day and said, here's the formula?
That's it.
And that was the whole lesson?
No.
Yeah, so what was around it?
It was in the middle of the lesson. She explained that she was talking about the organic chemistry and how is that machine. And then in the middle she talked about, okay, in the exam you will need this formula.
It was a side note.
Yeah.
Yes, I understand. Okay. You got this formula?
Yes.
Yeah. Okay. Sorry, Mishri?
Yes.
You have this formula? Yeah. Okay. So here's a simple enough question using the formula. I give you the wavelength of red light photon, and I want to know how much energy it has. So if you can take out your calculators, did you write down Planck's constant? Okay.
So only this multiplied by the velocity?
No, because this is the wavelength and you need frequency. Missionary, could you do me a favour actually? Could we take a picture of this lid so I can have it on my laptop?
Yes.
But could you
Could you use that now because his phone is
better quality?
yeah.
Oh, you have this calculator. You got the lid?
No, I don't have it.
Well, then it'd be useful for you to have this picture on your phone.
But you can't use it in the exam. Just check.
That's true. Although, if you wanted to print it out, I'm
You
okay.
can?
Well, if you let me know beforehand, because the other teachers might not understand, but I can explain it's okay. Yeah, let's just get it.
No, something
Yeah. And do one the other way around.
like this.
Yeah. Because my laptop is widescreen, so it might look better that way. Thank you. Okay. Try this one now.
Nano 10 to minus 9.
Got that?
That's the frequency.
Good.
By minus 9?
Yes.
9. not
Minus 9 for nano.
C3 to the power 8.
It's very small energy.
Yes. Okay, let's have a calculation here. So there's Planck's constant, can you see on the screen? There's Planck's constant, and I should multiply by the frequency. What's the formula for frequency? C over lambda, which is 3 times 10 to the 8 over 400 times 10 to the power of minus 9. So roughly,
7.5.
in total though, the final answer I got is this. Because this is so small, maybe we should put in electron volts. .1 electron volts.
Electron volt is constant on state.
Yes. Okay. Oh, I didn't realize I had parts. What is the frequency? What is the energy? What is the energy in electron volts? So we've done that now. Okay. Your mobile phone, this is true, your mobile phone works on a frequency of about 900 megahertz. This is roughly the frequency. It's different for each country though, I think. But it's about 900. I think maybe in some countries it's 1100. And the power output is about 4 watts for the signal. So, how many photons come out of your phone per second? Because the way you should picture it is the electromagnetic wave comes out and connects to the phone tower. This wave is at a frequency of 900 megahertz and the power is 4 watts. And I want to know how many photons there are. So you'll need to use 2 formulas here. You'll have to use the one for today, of course. Energy equals HF. And remember, this is the energy for 1 photon. And then you also will have to use power equals work over time. And here we're looking at per second. So it's 1 second then. So not too difficult. This will be a typical section A question in the exam. So I'll give you a minute to try it. You should be okay with it, I hope. So your first job is to get the energy of a single photon here.
Why are they coming out of the phone?
Because the phone is connected to the tower, like a radio.
Isn't it light? Photons?
Yeah, photons are not just for light, they're for any electromagnetic wave, like X-ray, gamma, radio. Light is the same as a radio wave. The only difference is the frequency. Finished?
I got the energy.
Good. So now how many photons per second?
So I have to multiply this work by the
Go on.
not the mass.
Oh no. Oh no. No.
Speed.
Oh no, way off. No.
What?
Now, let's first get the energy of a photon. So if I go back on the calculator, the only difference here is it's 900 megahertz. Mega is 6. So I'll just change this.
No,
No?
it's the frequency. You have.
Oh, I already have the frequency. Thank you, Ms. Sharif. So I'll just back. Like this. So this is the energy of 1 photon. Energy of 1 photon, 5.967 10 to the minus 25 joules. And this is the energy of 1 photon. Remember, power equals work over time, but time is 1 second here, so power equals work. The power is 4, so 4 equals work. So 4 equals to n times the energy of 1 photon. We don't know how many photons there are. What? So n is 4 over my answer.
4 watts or 4 joules?
4 watts. 6.7 10 to 24. What's that, about like 10 moles or something? How much is a mole? 10 to 23, is it? A mole?
Mole is the Avogadro number?
Yeah.
6.422, yeah, 26.
That's what I was asking. Yeah, so this is roughly 10 moles. Roughly. So that's per second how many photons are coming out of the phone. Yeah? Okay. Now, sorry, do you have this? Yeah? Okay. Electrons on the surface of a metal are trapped. They require energy to be freed. Therefore, they have negative potential energy. So, if you have a piece of metal, you know from electricity and from chemistry, there are electrons on the metal. But the electrons stay on the metal. They don't just hop off. They stay on the metal. So if you want to free the electron, you're going to have to give it some energy. So the electron is trapped. And if you remember, that means the potential energy is a negative. Yeah. So the electron is trapped. The energy that you need to free the electron is called the work function. So formally, the work function phi is the minimum energy needed to remove an electron from a solid to a point outside the solid. Usually the solid is a metal surface. Although technically it could be any surface, 99% of the time you're talking about metal surfaces because this is where the electrons are. So this is the formal definition of what's called the work function phi. If you can write this down as an exam definition. Yes? Got that? So just to note, the work function is a positive number because it's the energy you need. So the potential energy here will be minus the work function. When a photon strikes a clean metal surface, it will cause the release of electrons from the metal surface most of the time. If and only if the photons provide enough energy. This is known as the photoelectric effect. So what happens here is, here's my photon. What's the energy of this photon? The formula is HF. Here's my electron. Let's imagine the electron is freed. It has potential energy equal to minus phi. If the photon that hits the electron has enough energy, then we can free the electron. How much energy do we need? We need HF to be at least equal to the work function. Then we are given it enough energy to escape. When this happens, this is called the photoelectric effect. Interestingly, the photoelectric effect was discovered by Einstein. And this is actually what Einstein won the Nobel Prize for in physics. You might think Einstein won the prize for his formula, which everybody knows. It's not this. Einstein won the prize for discovering this photoelectric effect, that photons can free electrons from a metal surface. So most people would think it's because of his work on nuclear energy, but it's actually because of this. So please write the full definition down. Got it? Okay, good job. Here's an example of the photoelectric effect. We have, basically we have here a vacuum with two pieces of metal. The light comes in, hits the metal, and then frees the electron. And then the electron moves around in the circuit. And anyways, the electrons then make a circuit, and it could turn the light on or make the voltage increase or whatever. So if you have a low frequency and low intensity, that means not a bright light. What would that mean? That would mean some free electrons of low kinetic energy. Because just consider this. Let's imagine this was much bigger than what it needs. Then what happens is the extra energy goes into kinetic energy. If it has more energy it needs, it makes the electron move away faster. So, if there's a low frequency, then maybe some of the electrons are free, but not many. And if they are freed, they have low kinetic energy because they don't have extra energy because the frequency is small. And low intensity means the light is not so bright, so it means there's not many photons. Okay, so not many photons, low frequency means you get some free electrons of low kinetic energy. But what about this high frequency, but again low intensity? What do you think that would mean? Nope. Low intensity means there's not many photons, which means not many are freed. However, because of the high frequency, the ones that are freed very fast. So you have some freed electrons of high kinetic energy. Okay, getting the idea? What about low frequency but high intensity? Lots of electrons, with low kinetic energy then. Many free electrons of low kinetic energy. High frequency and high intensity. Many freed electrons of high kinetic energy. Now, in the exam, what I've seen them do a couple of times, they would have maybe a question for 1 mark, and they would say something like, the light is replaced by another light with the same frequency but brighter. What is the result? So if you replace the light with the same frequency but it's brighter, what's the result? What would happen?
Same.
Not the same result at the end. For the third time, you replace the light with another light of the same frequency but brighter.
That's brighter.
More intensity.
More intensity.
Yeah.
Many phases.
And their energy?
Same.
The same. So you have more freed electrons but of the same kinetic energy. Or if the exam question said the light is replaced by a brighter light of low frequency, well, maybe there's more freed electrons but they have less kinetic energy. And if the frequency is actually low enough, then there'll be no freed electrons because it doesn't have enough energy. So I think it's good to write this down. You don't have to write it exactly like this. I just need you to be able to answer that question in the exam if you get it, where they say if you replace the light with this, what's the result?
So what's the use of photo?
What's its applications?
Yes.
It is used as solar panels. Because if you think about it, these freed electrons that complete a circuit, they were freed from the energy of a light coming in. So you have a photoelectric panel on your calculator.
Yes.
The light hits the metal surface, the electrons are freed, and it completes the circuit. write this down? Okay. You wrote something good down? Did you? How's your mocha?
Good.
Is it? And your muffin? You're now not hungry? So no lunch today?
No, thanks.
Okay. Have you studied this before?
Not at all.
When's your test?
Wednesday.
You,
Math.
of course, what test? Yes. When is it?
The tutorial from 19th
19th?
February. Wednesday. And
Yes.
Thursday of the tutorial. And Friday.
Test. Okay, continue. So as a formula, you have it like this. Let's kind of prove this. Right, this is, let me break this picture up. Before, after. So you have your photon and you have your electron, and the photon comes in like this, and then afterwards the photon is gone because it hit the plate, and the electron now is free. So before the collision takes place, the energy here is the energy of the photon. What's the energy of the photon? HF. And then the energy of the electron. And what's the energy here? Yeah, but it's minus phi. Why? It's trapped. Afterwards, the photon is gone, and you have the energy of the electron. And what form is the energy here? Kinetic. Conservation of energy says that these should be the same. So you get this formula, which is what I wrote here. But usually in the formula book, and most formula books, they rewrite it so everything's positive. So you have HF equals KE plus the work function. Just take this to the other side here. This is how it would be in the formula book. This is what Einstein won the Nobel Prize for, which I think is interesting, is this formula. Okay, so this is something we'll need for a question now in a moment, if we can write this down. And I believe in the formula book it's written as the second way, all positives. Got that? Right. Here's one for us to do. The work function for copper is 4.7 electron volts. So that means the electrons have a potential energy of minus 4.7 electron volts. A photon of wavelength 250 nanometers strikes the metal surface. After the photon strikes the metal surface, an electron is freed and travels at a speed v. First question you can definitely do for me. I want you to convert the work function into joules. So that's the first thing for you to do, please. You know how to do this.
Multiplied by E.
Correct. You know what to do?
No.
23. Constant 23 in the calculator. So the first one here, and you do know it because you just took a picture, remember? Remember the pictures?
7.5 to the power of minus 1.
What did you get? 7.5, yeah. like this. Okay, that's part A. Part B, using this formula now, calculate the speed of the electron. So if you look here, do we know h? Yes, that's Planck's constant. Do we know f? Well, we do, because we have the wavelength, so we can know the f. Do we know the work function? Yes, we do. There it is there. The kinetic energy is a half mv squared. V is what we want. Do we know the m? We do. What number is it, Sharif?
Is it photon?
No, electron. So is that number 3?
Yeah.
So constant number 3 gives us the mass of the electron. And what else we need? What number is h?
6.
6 is h, yeah? Let's just double check that. Because there's 2 h's actually.
No, this is the part
Correct. Any other constants you need? Oh, and what number is c, the speed of light? It's written as c0 on the calculator.
28.
Okay, so there's all the constants. So give me the b, please. And I'll just write down 250 nanometers. So the wavelength is 250 nanometers. Okay, give me the b now. Who the heck is this? Yeah, I think usually it is, yeah.
Almost really good.
30028.
No?
How much?
110.73.
What did you get on that?
110.
Wait, do this.
Alright, I'll do it now. Right, what I'll do first, I think I'll rewrite the formula a little bit. So HF equals a half mv squared plus the work function. So HF minus the work function equals a half mv squared. 2HF minus the work function over m equals v squared. So v is the square root of this. So, square root fraction, 2 on the top, brackets, mass on the bottom. The mass is constant number 3. On the top, we have HF minus the work function. HF. Did I give you the F or did I give you the wavelength?
No, you'll get
So then I need to multiply this by C over constant 3? No.
25 multiplied.
What was the wavelength? 250, yeah. Times 10 to the power of minus 9. And then minus the work function. Yeah, I'll just recalculate it. Times 4.7. Right, we'll see who is right. Did you get this?
Near.
Yeah, what did you get then?
30028.
Yeah, okay, fine, yeah. Now, that is in joules. Oh no, sorry, what am I saying? That's in meters per second. So, if I divide by 1,000, 302 kilometers per second. Okay, continue. Right. The work function, this means the electron has energy equal to minus phi. In order to free the electron, it needs phi. If a light photon has exactly this energy, then the electron is just about freed, but it has no kinetic energy. It's just about freed. That is E equals HF equals work function. So what I'm saying here is, if you just want to free the electron, but you don't want to give it any extra energy, then you need HF to equal the work function. That means the frequency needs to be at least equal to the work function over h. So the minimum frequency, we call it f0. This is called the threshold frequency. Yeah. It's the minimum frequency to free the electron, known as the threshold frequency. So, yeah, if you want to make note of this formula, please. Called the threshold frequency. Yes.
Put it in the exam.
Oh yes.
What could they do that they can have?
Maybe you're saying what I was thinking.
No.
Why would I be doing something that's not in the exam?
No, I told them, don't be like the guy in our chemistry class who was stupid question.
Not a stupid question.
There's a couple of names that come to mind for potential candidates.
A couple of
like the Kepler law, not in the formula book.
Not in the formula book, but on the exam.
Yeah, so that's
That's what you meant?
that's why I asked. Like,
Okay.
why did I ask this question?
Okay. I believe Well, it's definitely on the exam, but I do not know if the threshold, I think this is also in the formula book. I think. Okay. Right, here's one for us to try. The work function for gold is 5.1 electron volts. What is the threshold frequency? Okay, so that's a short calculation, if you can calculate, please. And don't forget to convert into joules. What frequency did you get?
1.233 multiplied 10 to 15.
Correct. Good job. If the photon has twice the threshold frequency, then what would be the kinetic energy of the free electron? Okay, so now this is another calculation. It's just like the one we did a moment ago. The only difference is, well, I suppose it's a little bit, tiny bit different. We have HF equals 5 plus kinetic energy. And what am I looking for here? No, just what's the kinetic energy? So the kinetic energy would be HF minus the work function. But that's actually easy because I said the photon has twice the threshold frequency. And if you remember, the threshold frequency is what we need to free the electron. So we know that this is twice as big than what we need. And how much do we need to free it? Well, that's what the work function is. So I don't have to put in the numbers. In my head, I know that this is twice as big as what we need. So the answer is actually the same as the work function here. So it's the same answer as part A. Now, if you didn't believe me, you are welcome to put in the numbers and calculate the kinetic energy, and you will discover you get the same answer. But it's just much quicker to do it this way. Yeah? You don't look happy. I mean, you look happy on the outside, but on the inside I can tell you're not happy.
If I want to calculate it.
Oh, please. I'd be so happy if you want to. I won't stop you.
What is the F?
The F? You would have to calculate the F. Yeah, it has twice the F. Twice the answer from part A. The F is twice as big. So the F would be this.
This is the HF.
No, this is just the F.
So if we change the F from the same formula, that's what's going to be the same.
If you do what?
Change the F.
In this case, the kinetic energy is the same as the work function if the F is twice as big. But you could calculate this. If you can't see this, you can calculate it, because do you know the F? Yes. I just gave it to you. Do you know the H? Yes. Do you know the work function? Yes. Can you get the kinetic energy? Yeah. Watch. There's the F. Now I multiply it by the H. What constant was H? 6, wasn't it? Now, Sharif, I'm doing the thing you want me to do. And then minus the work function. And what was the work function?
5.1 multiplied by E.
Very good. And let's convert this back into electron volts. Boom. Same answer, as promised. Okay. What's wrong with you? You're happy?
Yeah.
How about we just keep going with these?
Just a 10 minutes.
No, do it.
Please.
Sharif, we'll finish in half an hour.
Tell me question.
But they're so short.
No.
I'm not giving you a 10-minute break, but I will give you a 5-minute break. You can take 5 minutes or not. These are your two choices.
Okay.
Of course. What do you have after this class?
What do you think?
I think maybe you're free and you're going home.
No.
No. Today until 5.
Today I'm